we knew there were 6 lines of shear reinforcement. So as long as they can expose the concrete, make good of the steel reinforcement, it should be fine. So that make good might mean when you do it, ultimately you need to put a carbon fiber wrapping or some form of fiber wrapping. There's other things called basalt fiber. I don't know whether you're familiar with it. So it's similar to carbon fiber, not as expensive. It's a bit stiff as well though. So you can use that kind of wrapping. So that was one suggestion. So along with that, we also said the road surface, which is like that, and there was a walkway here. We said the road surface need to be lifted off, and the lightweight topping has to be installed, because the road surface at the peak was nearly 30 centimeters deep in the middle, and it come down to about 23 on either side. That's a lot of weight for a very low vehicle count. So we suggested that they take this off and consider new alternatives, lightweight alternatives. That's where the tender stopped. We didn't say what. We can't really say what because we don't know. And if they come up with a concrete solution, I was happy enough with it. The other repairs included making good of the steel here, which has been damaged, and doing something to protect it thereafter. So all of that, all those patches underneath the structure were told to leave it like that. I'll show you. And that's where you guys, I need to dig into your. So see these patches? I asked them to leave it be, let it be. Why would I say so? As far as I'm concerned, steel in these slabs, it's a continuous slab anyway, but we assume for simplicity that these are the two end supports and these are the other end support, and slab just simply rests on it. And every joint was assumed to be simply supported, so the calculation becomes much easier. But either way, I knew those slab and the reinforcement in the slab has no meaning. And even if it corrodes, I wasn't concerned. Why wasn't I concerned? There's a particular force that we take in restrained slabs. So slabs that are, so assume there's a beam here and there's a slab in between the beam. Okay. As long as the span is reasonable to the depth, okay, I won't be concerned whether this slab has reinforcement or not. Any idea what I'm relying on? It's called compressive membrane action. So if you hold, so if you put loading, let's say you put, this is where we started the concrete. As I said, look, if you put the aggregates and pack the aggregates together, as long as your restraints are in place, you will get strength. That's relying on the fact that the aggregates are going to transfer the loading to the restraints, and therefore they're going to remain in place. Compressive membrane action refers to something very similar. So the loading that you apply here, let's say that's a tire loading here, will form some form of arching within the structure. And you need to have the depth to do the arching. So if it is nearly 3 centimeters, I think you need to be looking at 30 centimeters or more in depth. But that means if you have sufficient depth, the loading will be transferred under an arch form. Arch doesn't need reinforcement. It's formed within. And this is why we said, like, let it be, let all the corrosion spalls be, because chasing that means it's going to be a very expensive job. We knew from the beginning. And also if the spall decide to fall, it's probably going to kill a fish. We'll live with it. If a road was underneath it, that's a different story. And these are decisions that you will have to make knowing the consequences of it. Okay. Anyway, What other repairs would you suggest for a structure like that? Does it give you a picture of the structure, or do I need? I'll flick more pictures so you can see the state of it. While I'm taking you through the pictures, I'm looking for you to suggest more repair methods that you will apply to the structure to make good of it for whatever loading, 7.5 tons. Okay, so it's not obviously clear, but this is the edge where we had a big crack going up, and that's the leaching coming out of the structure. And this is where the cover was low at the bottom side of the structure, and not obviously clear or terribly clear here. So this is the bottom of the edge beam again, where the cover was exposed. You had some form of reinforcement being exposed. All of this is due to a low cover. It wasn't anything else. So you can see the line. This is the edge beam, and you can see the line, and that's throughout the edge beams. Southern edge beam completely had lines. There's still a line here, there's a line on the top of it. That's exactly where the road surface finish. So the water is just getting through, and that should be the other way around. And you can see the stains in the lines here. Okay. And it's not visible to you, probably not. This is one of the main transverse beam, and that spalling has, like you're talking about a couple of inch of concrete is spalled off. More staining, even more staining, a lot more staining. Different views of staining. We did do an underwater inspection, and it's part of that, just to see if the piers are okay, and below the piers are piles, so we wanted to check that the piles are okay as well. I think there's a good picture of the crack somewhere here. So we took cores obviously from different areas, and you can see the even a tape measure will give us an idea of the size of the bar, because we're not the people doing the inspection, somebody else is doing it. This picture is good. So that shows you the cover, okay, where it exists. And that is an underside view of the edge beam, and this is where the 4 reinforcement is sitting. Is there anything wrong with that reinforcement arrangement? They're so close together, right? So there's no space for concrete to go between them. That's because the edge beam itself was 25 centimeters in width. Okay, let's do a calculation. So they were 25 centimeters in width. Okay, so 250 is here. They had 4 of the 44 mil bars. Okay, how many shear bars? They had 6 of 12 mil shear bars. How on earth would they even achieve anything? So from starters, there was issues to be worried about. So this is what 4x4, 160, 176, 176 plus 72, 72. Okay. So 8, 4. No wonder they had issues. But it's a bit pseudo, because a bit later you had some sort of design into the, you've seen some pattern into the edge beam, and that pattern was projecting out, but they had reinforcement here just to keep the pattern in place. So it's only the lowest point, but that's a critical point. That lowest point, they had no way of escaping. On top of that, I said it earlier, they used river pebbles. There's no space between the bars. top of it, it's river pebbles being used. They are a different size and they're bigger and smaller and all of it. There's no way of getting down. And imagine 2.5 meter structure, and they're standing somewhere in the middle of it and trying to pour the concrete. Okay, so there's a big scaffolding or big timber structure below for them to stand and pour the concrete. Okay, so a person is nearly 1 meter plus at height, looking down at the structure to pour below this dense reinforcement. They had no chance. There's no way they could have done that. Because if you're standing here and trying to pour here with that much amount of steel in it. So even from the start they had issues waiting to happen. But they didn't really know much about concrete technology. But they knew about steels though. So they did a lot of good steel. Through the section, through the whole edge beam. So if you look at the crack, if you look at the core, you can see that the crack which is here is even visible at the far end. So it's a fully penetrating crack. Maybe I should have put that picture before. So that's the 1 meter walkway, and this is the surface, and that's your expansion joint below, and you can very visibly see the effect of it on the top. This is your small edgeway on one side where the water was falling to. And looking at the construction of the edgeway, it basically had a concrete slat, or basically a concrete beam, tiny one, non-reinforced structure. And you had the surfacing here, and they had sand. They had sand filling. So what happened is they took a long beam, which is like a brick, and they put it there in place, and then they put sand filling, and they put the surfacing on the top for people to walk, which meant that when water arrived, sand was happily taking all the water in and was holding it on, was slowly letting it out through the edge beam out into the structure. The reason they put sand is because you have utilities in there. You have the fiber optic connection, and you have the gas lines and all of that inside, and that's why they put that protection there. And that was doing more of the damage for us anyway in the future. So that was a part of it. So we had to then roll out the tender. In the tender we said to make good, to bring 7.5 tons capacity to the structure, 2 lanes have to be open, minimal repairs had to be done. Wherever we expected a shear failure that may occur, we had plates welded onto the structure, continuous plates over the piers, just so that kind of failures can be avoided in the future, because I don't know what 7.5 ton could really look in the future. If 2 lanes are open, people might take 7.5 tons more than they should fly. So, anything else I should have prescribed?
Does the crack size and the pattern, does it give any indication?
Yes, it does.
Like the size, because we are facing that touching the ground, the crack is lesser, surface it is more. Some cracks it is equal in size, in and out.
Okay.
Some pattern 45 degree, somewhere it is at 90.
So in this structure here, the cracking was due to few reasons. One was the construction joint. So every time they stopped and they started, there was exactly a crack, which will be visible a few years later. The second cracking is to do with the nature of the structure. So let me see if there's a quick picture that I can rely on. So this structure is built as a deck sitting on the piers. Okay, so the deck had 2 ladder kind of arrangement where you have 2 big concrete beams with the ladder arrangement here. But everything was sitting on the deck. Okay. But when you look through the piers, each pier, you will see the reinforcement was integral as part of the pier. So there's no way the deck would have moved on top of the pier. It was all part of the pier. And the pier stems were extremely rigid. Look at the pier stem. When we look at it, it's nearly 1.5 meter in width, and it's nearly 50 centimeter in depth. So they were massive pier stems. Top of that, they had these transverse beam was replicated a few meters below, close to the river level, so it was boxed. Okay. So that kind of extremely rigid arrangement, this is your structure essentially. A structure will undergo thermal or any other kind of stresses over its time. Where would it flex? So thermal stresses mathematically means you will expand during hot temperature, it will shrink during cold temperature. Where is it going to flex? So these are the piers holding on so tightly to the deck. To move horizontally. Piers won't move horizontally. It will go exactly where it is weaker. It was weaker up or down. That's what it do. So if you look at some of the cracks, you see bigger cracks here, right on the top of it, where there's normally we fear bending moment to be the maximum, but it was cracking on the top because it was just flexing up. It had no way to flex anywhere else. Flexing up, maybe it was flexing down. For us, the structural engineers looking at it, well, that's a bending crack. But when you look at the rebars, like there's no way it can bend. That much amount of steel simply can't do that bending, and there's no loading for that structure to bend. It was simply, this is called the integral bridges, where there's no expansion joint within the bridge. So the way this bridge worked was there were 3 of them. This was sitting on an abutment, and the abutment had a beam on it. So possibly that was allowed to move. I have no idea how detailed that is in terms of the approach span. So the abutment is here, which is a beam connected to the deck, so it's sitting on it. So that should have been simply supported, should have allowed some movement. But what I don't know is they had these kind of arches going either side to keep the soil here to be intact. That arch might have been connected to the beam, which means that movement is not likely to happen. That probably explained the inclined cracks we had in this side, which we thought was shear crack. Okay. But needless, so 3 of these massive structures, 20 meter spans, this is 20, 20, 20, can only move towards here, which had these kind of spandrel arches here, or move here where they put an expansion joint. Okay. I don't think it'll move anywhere near the expansion joint. That expansion joint was not necessary at that point because that structure had no way of moving. Okay, so this is where expansion joint theories, you need to allow it to expand. Okay, otherwise it'll do this job. And that was very much in line with all the cracks that you see on the road surface and as well as on the structure. So that explains the cracking. But this structure has stood its stand for 80 years, so we know structurally they're fine. It's just these cracks are inherent. If there was any crack that was expanding, then that would have been concerning for us, but it wasn't. We closely monitored, especially the shear crack. When somebody reports shear crack, you have to take it serious because it could be shear crack, and that's not something you really want in your structure. So we did take it serious. We considered putting a gauge, but because we were too close to the structure, we inspected it regularly. Okay. For new concrete, answering back to your question, for new concrete, there's a lot more forces in the structure. One is the thermal, what was the wording for thermal? It's just a curing. During curing, it produces differential heat, produces the heat basically. So it will have to let that stress out. Okay. If you have more cement, highly likely to stress out even more because it will produce quite a bit of the heat. So if your cement technology is not coherent with the thickness of the structure and the pore sequence, then what will happen is over a certain duration it'll just go to expand, but it'll sit because you have reinforcement in there quite often. It might have reinforcement, not sure. So that's one kind of cracking. The second is the moisture trying to escape, and if you have moisture buildup while the structure is still raw, it can accumulate the forces to get moisture out somewhere. Another possibility. If it's structurally mobile area, it might be relieving its stress by cracking. Cracking is the best form in which the structure can relieve the stress. So it might be just relieving the stress. None of that indicates the structure is bad. The nature of the force will tell which side will be larger opening or which side will be smaller opening. Bending cracks, we know it'll be larger at the bottom and it'll be narrower at the top. It could be so narrow at the reinforcement because of that compression that quite often we're not even worried about it, because it might go fast up to the crack, to the top of the crack, and then after that, because of the compression force, the diffusion will be very low. So it depends on the nature of the crack. But concrete technology could answer a lot of it, and structural movements could answer a lot of it. And all these movements are early movements, so it'll only happen early, and then once you leave it, it'll just arrest itself, be a happy position. Okay? So those are the things we suggested on the tender, and the contractor won the job because they part of the tender, our suggestion was to get rid of this, because this span was so damaged, and these tiny spandrel columns were so small that during flooding, this area floods. We have to check the flood region, and you can't even box this area because it is needed for accumulating that extra water, which comes at a force. And these columns are getting bombarded by logs of timber logs. So we were suggesting get rid of it, follow something similar. This abutment is equally strong as the other one, so we said, look, why don't you just continue this stuff? But the contractor came with a better solution. They took the deck surface off, the surfacing, they took that entirely off. They put a topping layer of 70 mil, 100 to 70 mil, 100 in the middle, 70 mil in the end, of lightweight concrete. Okay. With that, they made all these secondary beams redundant, and they transferred theoretically they can see that they transferred the loading to the transverse beams here. Okay. So that won the suggestion. That means we don't have to demolish this. Demolishing it is annoying because you have access to here,